Welcome to another edition of The Explainer. Today, we're looking at something absolutely foundational. We're going to unpack the hidden architecture of our physical world. Have you ever looked at the objects around you and just wondered why they behave the way they do? Well, today, we are breaking down the invisible rules that literally govern our reality. Okay, let's dive into this. It's the ultimate paradox, right? The kind of thing a curious 10-year-old asks that totally stumps you. Imagine you're standing by the ocean. You see a massive, towering ship made of incredibly heavy metal, just bobbing effortlessly on the waves. Then, you toss a tiny little pebble into the water, and bam, it drops straight to the bottom instantly. How does that make any sense? Well, this physics paradox is exactly what we're going to solve today, step by step. Section 1. The Sink or Float Mystery. Picture me as your friendly science teacher, in a classic blue lab coat, stepping up to the smartboard to demystify why objects do what they do in water. Let's start with a foundational rule. Density tells us how much mass is packed into a given volume. You see, it's not just about how heavy something is, and it's definitely not just about how big something is. It is the direct mathematical relationship between those two things. Section 2. Defining density and volume. Let's move to and see how this builds into something measurable. So here's the core formula. Density, which is often represented by the Greek letter rho, equals mass divided by volume. It really is that simple. If you want to know the density of absolutely anything in the universe, you just need to figure out these two numbers and divide them. And this brilliantly illustrates the whole concept. Imagine holding two blocks of the exact same size. One block is made entirely of cotton, and the other is a solid block of iron. Because they're the exact same size, their volume is identical, but their mass, completely different. The iron is fundamentally packed with so many more particles in that exact same amount of space, making it vastly denser. Section 3. Inside the particle level. Let's zoom way into the microscopic world to see exactly what's happening inside these materials. Let's analyze the physical makeup of three distinct materials: iron, wood, and a sponge. Look at how their particle spacing maps directly to their overall density levels. In the iron, the particles are tightly packed together, literally shoulder to shoulder, with virtually no room to move. That gives it the highest density level. Now look at the wood. The particles are noticeably farther apart, giving it a medium density. And finally, look at the sponge. It's full of empty air spaces, meaning there is very little mass packed into its volume, which gives it the lowest density of the three. So the crucial point is this: the closer the particles are packed together, the greater the density. It really is that straightforward. You gotta ask yourself, are a material's particles squished together like a crowded train car, or are they spread out with plenty of breathing room? That spacing dictates everything. Section 4. How to measure density. Let's energetically transition from theory to practice and head into the lab to see how we actually measure these invisible properties. Here's a brilliant three-step mini action sequence straight from the lab. First, you take your object and plop it on a digital balance to measure its mass. Easy enough, right? But what if the object is an odd shape and you can't just measure its sides to find the volume? Well, step 2 is the clever part. You drop the object into a measuring cylinder filled with water. As the object sinks, the water level naturally rises. By measuring exactly how much that water goes up, you've just cleverly revealed the exact volume of the object. And finally, step 3. You just take your mass from the scale and divide it by your volume from the cylinder. Let's try a specific calculation from the source experiment. Imagine our digital balance shows a mass of 200 grams. We drop the object into the cylinder, and the water displacement reveals a volume of 50 cubic centimeters. Okay, so 200 divided by 50. I'll give you a second to do the math in your head. 4 grams per cubic centimeter. This is exactly where the abstract math we just discussed turns into a concrete, measurable reality in the lab. We have successfully calculated exactly how much mass is packed into every single cubic centimeter of this object. Section 5. Density in everyday life. Time to bring the science out of the lab and back into the real world to finally answer our opening paradox. Now, what's really interesting about this slide is that the unbreakable rules of buoyancy all come down to a direct comparison against the density of water. Objects with a lower density than water will always float, like a wooden block or that cooking oil sitting in your kitchen. On the flip side, objects with a higher density than water, like a heavy stone packed tight with particles, will always sink. And there is the satisfying aha moment for our curious 10-year-old student. The mystery is solved.
You see, even though a ship is massive and incredibly heavy, it's designed with vast amounts of empty space and air inside its hull. This means its overall density, its average mass divided by its completely huge volume, is actually lower than the water it displaces. The stone, however small, is densely packed solid, making its density much higher than water.
Understanding the physics of our everyday life really changes your perspective. When you grasp density, you kind of stop seeing the world as just a random collection of heavy and light things, and you start seeing the beautifully structured particle architecture that governs how everything interacts. It's empowering, and honestly, science is just plain fun.
So, I want to leave you with this provocative final thought as we wrap up today's explainer. Look at the room you're in right now. Look at your desk, your cup of coffee, maybe the phone in your hand. Based on how they feel and how big they are, how tightly packed do you think their particles are? What is the density of the object sitting right next to you? Keep that curiosity alive, keep questioning the physical world around you, and I'll see you on the next explainer.